Continuing on here, we're moving on to some algebraic questions. This is going to be something that we're going to see a lot in this unit. A lot of basically those questions where you're deriving an expression in terms of variables that you're given. So let's start here with the situation with Bobby Clark and Gordie Howe. So we have Bobby Clark and Gordie Howe are skating towards each other. And we know that they collide over a period of time t. And we know Gordie's initially move at some speed v, and after the collision, speed of Gordie is 0. Bobby, we don't really know anything about his speed. So the first question asks, what is the acceleration of Gordie Howe? This one actually doesn't require anything about forces. This one simply requires some information about kinematics. We know that the initial velocity of Gordie is this speed here, v. We know the final velocity is 0 because he comes to a stop. And we know that our time here is t, so we can solve for our acceleration. So I would just use our trusty acceleration as vf minus vi over t, which means it's going to be 0 minus v over our time t. And so we end up with an acceleration here of negative v over t. Okay. If you had said v over t, that would be acceptable as well. Either one works in this case because I didn't specify magnitude of the acceleration. I just said what is the acceleration. Moving on to part B here. What is the acceleration of Bobby Clark? Well, if we think about Bobby Clark, we really don't know much. We don't really have enough information about kinematics in order to be able to solve this. We do know the time would still be t, okay, but what we don't know is we don't know the initial velocity, we don't know the final velocity, we really don't know much. However, we do know that when these two objects collide, as in any collision, they experience the same force. So what I'm going to think about here is my sum of the forces equals ma. So if we think for a second about the forces acting on Bobby during the collision, we have the force from the ice or the surface, we have the force of Earth, but most importantly we have the force of Gordie on Bobby. And we have the same set of forces acting on Gordie. We have the force of the ice, the force of the Earth, and of course the force now of Bobby on Gordie. These are the two forces we really care about. Those are our equal and opposite pairs. So let's go ahead and think about our forces in the x direction and set those up for each person. So for Bobby, we have the sum of the forces is equal to ma. The only force acting horizontally is the force of Gordie on Bobby. And that's going to be equal to the mass of Bobby times Bobby's acceleration. All right, and for Gordie, we have sum of the forces equals ma once again. Only force in this case is the force of Bobby on Gordie, and that's going to be equal to m times this acceleration here, negative v over t. One last little important piece that we can get from the problem, and that is that Bobby's mass is 1.5 times what Gordie's mass is. So that means that down here in my equation, I can say that this force of Gordie on Bobby, is equal to 1.5 m times a. Okay, I'm going to bring these two forces together here. I know that these two forces are equal. Just one is going to be negative because they are pointing in opposite directions. So I can say 1.5 ma equals negative m times negative v over t. And that just comes from Newton's third law. The forces are equal but opposite, and that's where that negative sign comes from. So I can go ahead and divide out the m's. Okay, the two negatives on this side just make it a positive, so I get 1.5 a, where a is the acceleration of Bobby, is equal to v over t. And I solve for a and get that a is v over 1.5 t when I divide by 1.5, or, okay, v over 3/2 t, which really makes this, multiplying by that reciprocal, 2/3 v over t. And so there I have my answer. And that makes sense. My initial acceleration was v over t. Bobby has more mass, so he should have less acceleration. That's what Newton's second law tells us, that mass and acceleration are inversely proportional. Okay, and so there's my answer. Obviously, if you have a negative, that would be okay. It all kind of depends on what you set up as the initial direction. Moving on to the next one here, we have a bunch of forces here acting on this rocket man. We want to derive an expression for the horizontal and vertical acceleration. So the first thing I'm going to do here is I'm going to take these forces at angles and break them into components. So this x component here is going to be F wind cosine 35. The reason why it's cosine is that this is the adjacent side here. All right, and then the opposite, the y component, is going to be F wind times sine of 35. And the reason, once again, there is that this is the opposite side. Doing the same thing for my pushing force, breaking that into its x and y components. So we have on the x, F push cosine 22, because that's the adjacent in this case as well, and F push sine of 22, because that's the opposite side. Once I have that, I'm going to my trusty max and may. So in the x direction, the forces I have the force of the wind times cosine of 35 minus the force of the push, and I'm subtracting it because it's going to the left. Using that standard sign convention, things going to the left and down are negative, right and up are positive. So that's what I have for the sum of my forces. I've replaced, remember that's always our goal, replacing that left side of the equation. And so that's going to be equal to m, the mass of the rocket man, times his x acceleration. And I ultimately want to solve for that x acceleration. So I end up getting that the x acceleration is simply force of the wind, cosine 35, minus the force of the push, cosine 22, all over m, the mass of the rocket man. And now I have it solved for in terms of mass and the given forces. Moving on to my y, the forces I have in the y direction, I have that F wind sine 35, I have F push sine 22, and I have the force of the earth. And that's going to be equal to m times my y acceleration. Okay. Once again, solving for that acceleration, I get that ay is equal to force of the wind sine 35 plus that pushing force times sine 22 minus the force of earth all over my mass, which is just m. So there we have it, an expression for both the horizontal and vertical acceleration in terms of the forces and the mass. All right, moving on to this plane problem. Once again, I'm going to start out by doing the components of my forces. So I'm going to just draw this down here so I have enough space. So I have one force here, F1 at an angle, and so the components are going to be F1 cosine of 22, all right, because that's my adjacent side, and F1 sine of 22. So next step, we're going to go ahead and set up my max and my may. So in the x direction, I have this F1 cosine 22. And that's going to be negative because it's going to the left. At least that's what I'm going to say. You just need to be consistent with those forces, as always. And then we have the force of the wind going to the right, and that's going to be equal to the mass of the plane times the acceleration, which in this case is actually given. We're told that it's accelerating at a rate of a, and it's going to the left, so I need to make that a negative. So I go ahead and I ultimately want to find an expression here for F1, which I can actually do with this piece, okay, with this equation. So first I'm going to move that F1 cosine 22 to the other side and move this guy over to that side. So I end up with F wind plus MA, and it's positive because it moved over, equals F1 cosine 22. So that means that F wind plus MA over cosine of 22 are equal to F1, force 1. So there we have the first part. We got that from my max. Now I'm going to go ahead and set up my may and see what information I can get from that. In the y direction, I have this F1 sine of 22 going up minus F2 going down, and that actually is going to be equal to the mass times my acceleration, but I'm told that it is not accelerating vertically, so that's just 0. What that means is that F1 sine of 22 is equal to, this whole side is 0, so is equal to just F2. Now, I'm not quite done my answer because I do notice it says answer in terms of ma and the force of the wind, which I did not do. Okay, so what I'm going to do is I'm going to take this expression I got for F1 up here and plug it on in. And so when I do that, I get F wind plus ma all over cosine 22. So there's just that F wind term that I'm substituting, or F1 term that I'm substituting in here, and then that's going to be times sine of 22 equals F2. All right. Now we do have it in these terms that were defined up here. We can do a little simplification. Some of you may recognize that sine divided by cosine is simply tangent. And if you do, then you can use this shortcut. If you don't see that, that's obviously quite all right, but we could rewrite this. This answer would be acceptable, or we could rewrite it as FW plus MA times tangent of theta equals F2. So that's just getting into a little bit more pre-calc stuff than maybe you are at this point in the year. All right, moving on to my next problem. Once again, I'm going to break any angle vectors into the components. So we have this force of the string going up at an angle. I'm going to break it into x and y. I know that angle theta is the upper angle, which means that x now will actually be sine of theta because it's opposite that angle, and y is going to be cosine. The first thing we want to do is we want to derive an expression for the magnitude of the force from the string. Okay, so as always, and we shouldn't even think twice about this at this point, I'm going to set up max and may. So in the x direction, I have Fs sine of theta, and that's going to be equal to the mass of these fuzzy dice times their acceleration, which I know actually is a. I'm told it's accelerating to the right at a rate of a. So I could go ahead and I could solve for Fs, but I'm still going to have this theta term in here. All right, and it says to answer in terms of MA and FE. So I'm not going to worry about that quite yet. I'm going to go ahead and set up my y. And so in the y direction, okay, I have this Fs cosine of theta and minus the force of the earth, and that's equal to the mass. And once again, my acceleration is 0. It says it's not accelerating vertically. Okay, so I can say then that Fs cosine of theta equals Fe. Once I get to this point, I do have a few options. Okay, there's a few weird mathematical techniques I can use, but ultimately I want to get an expression for that force of the string in terms of M, A, and Fe, not theta. So this theta here needs to go away. So here's what I'm going to think about. This right here is really the x component of the force from the string. And this is really the y component from the force from the string. So I can say, if I'm thinking about my force of the string, I can say that this x component is simply ma. And this y component is simply fe. Because these really were expressions, right? Fs sine of theta. That is the x component in this situation because theta is that upper angle. This Fs cosine of theta, that is the y component because it's equal to the force of the earth. So what I can do now is Pythagorize this and put these together. So I have a squared plus b squared equals c squared. So ma squared plus fe squared equals c squared. And I can solve for c. So C, the hypotenuse here, is going to be equal to the square root of MA squared plus FE squared. And so that there is my answer to part A. That is the force of the string. And you could rewrite it like that underneath. For part B, it says derive an expression for the angle, this upper angle here, okay, in terms of MA and FE. So what I'm going to do is I'm going to say the tangent of theta equals opposite, in this case MA, over adjacent, which in this case is FE. So I can solve for that angle, and I get that that angle is the inverse tangent of MA over FE. So we're doing a lot of the things that we would normally do with vectors when we know the components, and that's what we found here, right? And we're trying to find the magnitude and direction. Once we know those components, we can do Pythagorean theorem to get the magnitude, which is the hypotenuse, and we can use some inverse trig to get the angle. For this last one, we're asked what would happen if the acceleration of the car increased. We want to just simply describe the changes, and I'm actually just going to describe all three of them all at once. Okay, so we're looking at the changes to the angle, the magnitude, and the vertical component. Okay, so if acceleration increased, then the x component of the force of the string, Fs, would increase. So that's the direct change that happens when we increase that acceleration. So what effect does that have on the angle? Well, the angle would increase, and we could think about the equation that we just derived here for the tangent of the angle, or we could just look at this visually. All right. If we think for a second, if Fs goes from there with that particular x component, and we increase that x component, and I'm really going to exaggerate this, okay, we see that the angle here is obviously more than the angle there. Okay, so by increasing that x component, we increase the angle. The other thing we do is we increase the magnitude. Okay, we increase the overall magnitude, and once again, we could see this from the equation that we've just derived, which is over here. So increasing this term here is going to increase the overall magnitude. Or we could look at our picture. Right? We clearly can see that this hypotenuse and this hypotenuse are not the same, and this one is more because it has that increased x component. Lastly, we're asked how the vertical component of the force of the strain would change, and the answer is that would be the same. Okay. In both cases, that vertical component needs to balance the force of the Earth. All right, and we see that here with this equation that we derived. But what that means is there's no change to Fe, so that y component is the same.